Assalamu alaikum. Uh, I am MD Salam Reza Jeevan. Today, I will give you presentation on the presentation topic integrated passive device technology for biosensor applications. Myself, Salim Reza, and I'm going to present this presentation. So the first of all, we will just talk about overview of how the integrated passive technology came in our in the technological development. In 1965, George Lee Moore had proposed a Moore law. It basically known as Moore law, and this law is a state for the number of the transistor in the per square inch on the integrated circuit has just doubled around after 2 years. This law basically introduced a new term in the semiconductor technology, is the integration, the term. Basically, this term defined as the compacting or integrating a lot of chip or devices into a single wafer or in the single substrate. This is actually integrations. And for these integrations, basically reduce the system sizes and also improve the performance. You can see the right hand figure. In around in 1970 to starting from this period, 2018, is the series semiconductor, and after it's going to happen by the conducting in the nanotube transistor, and after that the one single atom transistor. That means it's going the decreasation. This is actually basic law of Moore law, which state that. And in the RF technology, the compact semiconductor are largely used. Basically, the commonly use of the compact semiconductor are gallium arsenide, indium gallium arsenide, and indium phosphate. This compact semiconductor are used to produce the fabrication for the RF system because of a high electron mobility, good insulation properties, and powerfully avoiding the capacitance and inductive loading compared with the silicon substrate at a high performance. Basically, this compound semiconductor are developed to integrate for the IF devices, and these IF devices applied for the RF biosensor. And also after that, a new sensing IC technique is the monolithic microwave sensing has just came to fabrication RF active and passive devices in a single substrate. This is the one type of photograph with a gallium arsenide monolithic microwave IC with a 2 to 18 gigahertz R2 converter. This is actually. And growing the demand of recently in the RF and microwave application systems are going demand day by day because of the low cost technology and high efficiency of manufacturing. So many of researchers are just devoted to study a way to improve the system performance and try to reduce the cost and try to reduce their sizes. And this happened by this IPD technology, integrated passive device technology. Basically, this possibility of integrating device are allowed to one device or module achieved by the IPD manufacturing, and which is integrated to different registers, integrator, and the capacitor into single devices. And if we talk about to the wireless communication module system, it also helps to produce the and uh, the passive devices applications or balance filter, band pass filter, band stop filter, and the RF micro resonators. This IPD technology actually offer to compatibility between the passive devices and to the active devices within the same device, and also the effective for the biosensing. So that's why it is important for IPD technology. And the increasing interest, the day by day the design is going on. So the design of the glucose sensor are including the RF technique is uses. There is a rhythm, the possibility of easy fabrications and short asset time, and the modulator free detection in the microwave spectrum region. That's why the researcher has just to interested to the RF sensing technique to the development of the glucose sensor. And after that, the researcher are just focused on the RF biosensor supporting because of high throw output and also the stability of the non-invasive applications, and also the non-destructive detection capabilities with a less power consumption. That's why they are focused on this technology. And researchers also focused or proposed a sensor implemented with a band stop characteristics with a high attenuation, having a discrete performance in the its band. So that's why the proposed technology has just very going interested. And the sensor designed it with a YAR-based capacitor, and these types of capacitor is called as the metal insulator semiconductor, AMIS capacitor. And this also provided this technology flexibility to the sensor, and testing time of minimum with the analyte. Basically, in the test time, need to be minimum amount of analyte to sensing and helps to the sensing the sensor in the sensor sensing time. Basically, we can see a 3D representation of one kind of a micro resonator based ER-based model structure. The first design implemented the moderator fault black type resonator, in which the second metal is the fabricated on the top of the first layer, and which form the ER cavity responsible for microcapacitor. You can see in the 3D structure, the top layer is by the AU layer, and this is the gold plating layer, electroplating layer, and this is also a layer of Si2 and 3, and this is also gallium arsenide layer, and there are the cavity. There is a cavity. So this is the 2D view, 2D view. You can see, and the top layer is electroplating with a gold. This actually using the gold to remove the necessary oxidations, and this also enhance the immobilization of the glucose molecules to provide the excellent stability at the sensing time. So that's why we use this as a gold for the top layer by the electroplating. You can see the layer simulation of the layer information of this the glucose sensor. and the bottom layer is the gallium arsenide layer. Basically, this the fabrication process or some fabrication process is a start with a preservation layer. Preservation layer uh, uh, by the compost with a Si annex. It actually deposit on the top of the gallium arsenide, almost 2000 Amstel, and this is happened by depositing of plasma enhanced chemical vapor deposition method using. This is also necessary because of to gain the even surface over the defect and the roughness of the substrate surface. After this deposition, a chemical beam electrovapor nickel chromium layer also deposit on the target composition by the 90% of the nickel and 10% of the chromium to get a optimal performance. You can see the layer information of the practical layer by this. There's also layer order. This is all. These are the layer. These are the layering measurement in the nanoscale, and micrometer one is a micrometer scale. And I just summarized the whole process by the arrow. The first layer going to the preservation layer, and after that, this is also happened by the PECV, the plasma enhanced chemical vapor deposition, and this is also by the electropotoling beam and this is also after that it is a marking by photoresist photoresistor, and after that the thallium or aluminum metal layer is just metal layer is just to be produced, and after that RIE reactive ion etching is provided with CfO2, and this after that the etching process a 1000 ounce tank the thickness of the aluminum seed layer is produced, and after that air breeze photo process they happen, and by this after this process the electropotoling process is also happened for the gold gold electropotoling, and then the 3000 Amstel silicon oxide to protect for the oxidation and moisturize. Basically, in this process, a MIM capacitor is formed to the bottom of the first metal and the second metal of the top plate, and between the dielectric. You can see before going to see this is the whole process laboratory of the Korean Advanced Nano Lab Center. This is the whole process, how the fabrication process going on. And this is the IPD fabrications and measurements of the line. This is the different technique. The first was the PEVCD, plasma etching chemical vapor depositions. After that, the FIP and testing and measurement, and IPC of etcher and electron beam, and also the stepper. And you can see the whole diagram of the process of the IPD technology for device, the several steps. And the first steps, we just deposit of a preservation layer on the top of the gallium arsenide layer or substrate layer, the NIX for this layer. And after that, we are just putting of a nickel chromium layer for the TRF as a contact to the after in the step 2. And in step 3, we are just to deposit a photoresistor on this layer by the marking process. And after that, in the step 4, we to deposit by electron processing of evaporation. Thallium or gold bottom is just like as the figure of the yellow color distinct, This is the titanium or AU produced, and this is also basically a conduction between this two layer, and this is also form a resistor. Yeah. And after that, SiNX is via open photoresistors and also produced in the 5 step. And after that, to etching process, a MIF capacitor is formed between them. That after in the 6 phases, in the step number 6, and in the step number 7, the TI proceed before to the going to the top layer depositions. We just seed a pseudo metal layer on the yellow color. The top layer, the yellow color is the seed metal layer is deposit. And after in the 7 in the 8, we are just to produce year-based photoresistor to producing by the year-based photo post process. And the after that, in the step number 9, the chromium and gold top metal by electrobottling process. You can, the orange is the one of them. Basically, after this process, we can see here there is also produced a resistor. Is the nickel chromium resistor, the nickel chromium resistance, and this is also a produced a capacitor. Is the MIM, is the metal insulator metal capacitor is produced between these two metal, and this is also insulator, act as an insulator between them. And this is also your cavity, and here is also produced a metal insulator and semiconductor capacitors is produced. On this, you can indication that, and this is also the view of the practical view, the simulation view. And here you can see the substrate is the gallium arsenide, and the first metal view is the blue, is the blue color, and that these are the this is our the film first metal layer, and this is also the air breeze the layer, air breeze post. These are called as the air breeze post, and IBM is basically a air breeze metal. Is the top metal. Is the orange color. Is the orange color top metal, and this is also a practical view of this cross-sectional view of this. And with this technology, there's a lot of advantages. So what is the future of the IPD technology, IPD technology? Basically, with the thin film of the IPD technology, these are going to be developing day by day in the semiconductor industry. And because these are also uses in the RF technique, and also uses for the high brightness lead producing, and also uses for the digital and mixing signal application also. Basically, this this technology uses for the replacing the bulky, decreasing passive device component, which is robust, and also it is also the high cost and also long time of processing. That's why the IPD technology is growing interest. And the most important thing is that the integrating of various devices into the IPD technology in the front end and back end, there's a lot of challenges to be came from. The major challenges is to the integrating a lot of devices in the same device or same substrate to down the performance. So it is the major challenge. So how to improve this performance? And while the manufacturing to be, it also the cost also the increased, and also the processing time of this technology is also increased with this complexness of the design. So that's why it should be a major challenge for the IPD technology. To solution of that, we have to use the accurate simulation and verification to going to the fabrication process. This also helps to the IPD technology as a successful fabrications. And with the help of with the increasing the die size, die size is increase, die size is decreased. So the compact of the devices into the same wafer or same substrate or die is also very complexness, and the component increase also interact with the individual component. So that's why we ignore the RF and microwave frequency because they interact with each other when we fabricated a lot of devices in the same technique. So this is also another challenges. And in the conventional technique, fabrication technique, the lump component library model is also used, which cannot the longer the predict the accurate the devices simulation. So that's why it also a to cost high cost and also time consuming process. That's why there is a lot of design to be issues to be remembered, and this IPD technology has just relief from that. And in the IPD technology, basically coming from the benefit for the coming with a IR bridge optimization for the capacitor has obtained it and show the reasonable result for the glucose sensing sensor technique. But cavity, we're talking about the cavity, it is not close enough sustained volume in the glucose so we have to necessary step and design and manufacturing must be implemented to design this and close to close type cavity so that we can accurate the model and figure out the amount of glucose level in the human sweat, or also we can detect the D-glucose solution from this. So I hope the IPD technology and advance of the passive integration of the technology that can improve the degree of integration and simply the assembly highly desirable for RF and micro applications also. Thank you all to listen my video.